Section 12.3 is about, I'm not going to do that underline today, is about something called polar coordinates. And so the general idea is that integrating over circle or circle-like regions is difficult using Cartesian. That's just your normal x, y coordinates. And so we want to switch to polar coordinates. And so up to now, when we look at 2D coordinates, double integrals, we have some f of x, y, and we integrate over the region dA given by dy dx or dx dy. And we're going to turn that into an integral over the exact same region, but now we want our f to depend on variables that we'll call r and theta. And our region dA, our quantity dA is actually going to be written r dr d theta or r d theta dr. Both of those things are okay. And when we write r and theta, what we're saying is that in our normal xy system, if there's some point, it can be given by the coordinate xy. So there's the x and there's the y for the point, and you could write, I found it, it's xy. But in our new coordinate system, we're going to denote that point by r theta. And the way we find the values r theta for this point are that we draw a line from the origin to that point. And r tells us how far you are from the origin. And theta tells us kind of how far you are from the x-axis. It's degrees counterclockwise from x-axis. So that'll be our new way of orienting a point xy, is we'll say, instead of how many units right do you move and how many units up, we'll say how far do you travel from the origin and how much do you sweep up from the x-axis to hit the point. And what this is going to turn into is a bunch of substitutions. And so I want you to write like this list of things somewhere handy. And you might even want to put them like at the front of your notebook and leave space for 2 more sets of things like this when we cover the next couple sections of class. But instead of dA, which would have been dx dy or dy dz, dx dy or dy dx, you're going to replace this with r dr d theta or r d theta dr. Either one is fine, just changing order of integration. And then any x value you have becomes r cosine theta, and any y value you have becomes r sine theta. That just comes from like a little triangle here using your trig relationships. You're used to doing this kind of thing for like force decomposition in your engineering or physics class. So the vertical component has to do with sine is opposite over hypotenuse. Hypotenuse length is r. So your y height is r times sine theta. Same for cosine theta, except that it relates to the adjacent length, so horizontal. And then one other important relationship that's sometimes easier than using those two things separately is that the quantity x squared plus y squared is the same as r squared. So when you live on a circle, it's the equation x squared plus y squared equals r squared. You can just use that substitution anytime you want. So we'll use this a whole lot. Making the substitutions tends to be the hardest part of this type of question. So to convert to polar coordinates, you need to do all four of these things. You need to change f of xy inside your integral into f of r theta using substitutions. Whichever ones are easiest, use those. You need to write dx dy or dy dx as r dr d theta or r d theta dr. Please do not forget that extra r that you put out front. And then you need to convert old bounds, like a less than or equal to x less than or equal to b, and c less than or equal to y less than or equal to d, into polar bounds. A, B, C, D, E less than or equal to R less than or equal to F, and F, G less than or equal to theta less than or equal to H. Important notes here. Inner bound can still be a function of outer variable. It's very hard to think of functions of distance. So more often than not, it's going to be that your bounds for r are a function of theta. Kind of imagine drawing like a spiral. How far out you go changes with how far you've traveled in theta, things like that. Just better than what I drew. So that's still true that, you know, your bounds here could be E a function of theta and F a function of theta, or the same for theta a function of R. It's just those are much more difficult to come by. So I'm going to write this one right here. And then the way we think about the bounds can be a little bit difficult. So bounds for R go from closest to origin out to furthest from origin. So remember when we thought about bounds for x, for example, we thought about absolute furthest left and absolute furthest right. Now our lower bounds for r are going to be as close to the origin as you can get, and our upper bounds for r are going to be as far from the origin as you can get. This being very close, this being very far. And then theta goes from furthest clockwise from x-axis out to furthest counterclockwise. from x-axis. So just to draw a picture of what I mean, you're going to start like as far back as you can go clockwise, and then as far forward as you can go counterclockwise. Oops. And that'll make more sense when we start doing examples. Bounds for theta tend to be the easier part of these problems. And then the fourth step is that you still have to evaluate your integral. Just like regular calculus, hold one variable constant, integrate the other, but remember to include your r from part 2 as a variable. So don't forget to multiply that r through and include it in your integration. It is a variable here. And we're going to do a whole bunch of examples.